William Shakespeare wrote, "What's in a name? That which we call a rose by any other name would smell as sweet." He was implying that the naming of things is irrelevant. Giving something a name doesn't change the thing itself, and the thing can have more than one name. Naming is very important when we want to refer to a particular thing. In this series of videos, I'm talking about networks of computers. We need some way to designate a particular computer we want to communicate with. This could be a low-level address, like a 48-bit Ethernet address, or a 32-bit Internet Protocol version 4 address, or it could be a user-friendly name, like a domain name. Before I get into the detail of how naming works on the network, I'll say a few words about namespaces in general. By naming, I mean anything that designates a particular object, a computer, a building, a person. This could be a number or a string of characters, or it could be a random string, or it could have meaning in other contexts. The name could be structured. The structure could have meaning. In the non-computer world, we see many namespaces. Usually the name is not unique and needs other elements or structure to disambiguate. This extra information is a form of metadata or data about data. A good example of a name that often is not unique is a person's name. In the United Kingdom, there are over 500,000 people with the family name Smith, and a large number of those have the same first name. Clearly, we need more information if we want to send John Smith a letter. We need a postal address. List of a number of parts in a hierarchy, starting at the least significant part. We have the person's name, then we might have an apartment number, then we might have the street number and the street name, then a suburb, and then a country. Many of the parts are also not unique. There are over 16,000 streets in the UK called High Street. But when we combine them in order with other components of the address, we can see where our John Smith lives. Street addresses in other cultures can be very different. For example, the Japanese system. If you're interested, search for Japanese addressing on Wikipedia. Globally unique names and hierarchical names are not the only form of name. In a computer network, there is another unusual form of name called a source root name. So, for example, if we know the name of a person or an object is not unique, rather than use a hierarchical address, like the street address I just showed you, we could specify a route to get to the person and use that as the address. So we start at the source and we might say, head down this street, turn left at the fork, right at the big tree, and so on. And this gives us a form of address for finding someone. But this means the object may have many possible addresses depending on where you start and the route used to get there. Now, this might seem very odd, but in the early days of the Unix operating system, there was a widely used email and file transfer system called UUCP for Unix to Unix copy that used addresses like that. And you can see them here. In this case, your message first went to big host, then it went to somewhere, and then it went to my computer before it got delivered to the end user. Now, in a modern computer network, we have namespaces at all levels. There is the 48-bit globally unique Ethernet address, the 32-bit Internet Protocol version 4 address that has a global and local types of addresses, and we've got the 128-bit IPv6 address. These could potentially give every atom in the universe a unique address. Above that low-level address, there are computer or host names, and then hierarchical domain names, which I'm going to talk about in more detail. Then there are sub-addresses or port numbers for services inside the computer. In applications such as email, we also have usernames. So there are many different namespaces, and they all combine to designate a particular thing. In the very early days of the internet, which we called then the ARPANET, computers on the net had a 24-bit address. They also had corresponding simple names, just a word. and these were human-friendly. The names and these addresses were stored in a single file called the hosts.txt file, and these were distributed at regular intervals to computers on the net. At that time, there were only a few hundred computers on the network. This is a fine way of distributing the name-to-address mapping for a small number of network computers, but it certainly won't scale to the millions of machines we have today. In the late 1970s and early 1980s, the network was growing rapidly, and new protocols such as IP version 4 and TCP/IP were in development and soon to be deployed. A better solution was needed. So, in 1983, a more efficient system was developed, the Domain Name System, or DNS. Apart from necessary security and other minor updates, the DNS remains essentially the same today. This is very impressive, given it was designed and implemented by one person, Paul Mockapetris, and you can read about that if you look him up on Wikipedia. The main reason the old system was inefficient was that it was centralized. We had that one file, the hosts.txt file, that contained all the name number mappings for the entire network. And updates had to be done via a central system. The entire list was then sent to all machines. The way you got a new machine name registered was to ring, on the telephone, a person at a central system in Los Angeles and give them the name to put on the host.txt file. They would then enter it into the file, and the file would be distributed to all the machines on the network. Clearly, this is not going to work in today's internet. The key to improving the efficiency of the name update and lookup was to make the service distributed. Instead of looking in a single file in your system that was only updated occasionally, in the DNS you add your new host name to a local server, and then to look up other machine names, your local server sends a request via the network to remote machines that have the necessary information. Well, how does this all work? Well, domain names make up a tree hierarchy. So if you have a name like www.sydney.edu.au, then you can see that this is a series of parts with the particular machine, www, here on the left, and the city or the institution it's in, and the sort of class of institution and in the country. And this makes up a hierarchy. It's similar to a file path name, but written in reverse and using dots to separate the parts instead of slashes. Also, we don't write the root of the tree. We don't write the dot on the right-hand side. You could, but in fact it's usually left off. Now, incidentally, in the early days of the internet, when this system was first being developed, there was a debate about the ordering. The British wanted the same order as file path names, most significant part first. The Americans wanted the reverse, like street addresses with the most significant part last. The Americans won this debate, as we now know. The sequence of names forms a tree, like this. And different levels can be given meaning, such as the country code. Now, in fact, the initial domain name service had that top level as being country codes or classes of institution, like .com or .edu. But these days it's now possible to get any name at all at that top level, so it's not just country codes anymore. The way it works is that each level on the hierarchy there are computers that run programs called name servers, and they run they handle the information for that particular level and maintain name information about the level below. So in this excellent diagram from Wikipedia, you can see that each of those circled parts here, these ones, each of those is a particular zone of the internet, and each one is handled by the machine here at the top. That's the name server for that particular zone. And if you want to find out information about nodes inside your zone, then you consult that name server. Now, the name server also interchanges information with higher level zones, higher level name servers. And so at the ultimate, if you didn't have any information at all, you'd go to your local name server, which would consult the name server above it, and so on, right back to the root of the tree. Now, of course, they make it more efficient than that because there is a lot of caching going on, where information that's looked up once is kept, and you just get it from your local machine again. The way they keep that up to date is that the cache has a timeout value, or the particular entry has a timeout value, and when that's exceeded, it fetches it again. When you start up your computer, it gets network configuration information, typically using a DHCP server, and this gives it the IP address of the computer. It also gives the IP address of a name server to use for DNS lookups. The DNS protocol, the exchange of messages between your client program and a name server, is done using the UDP protocol, which I've talked about before. The DNS is a very simple database of text records. Each record is just a line of text. And we call these database records, these lines of text, resource records, and they contain information related to some name. But the basic information that's stored is the name that the record is relevant to, the type of record, what type of information the record contains, the class. This is really historical because there's only one class that's in wide use, and that's one called IN, which stands for Internet, because in the early days they envisaged that this same system would be used for other networks which have now disappeared, other network protocol types. There is this TTL. Remember I mentioned that a lot of caching is going on. TTL is time to live in seconds before this record expires and has to be refreshed. And then there's a length of the amount of data in the record. And finally there's the data field itself, the text for this particular record. These different types of record are very important. The basic types are A for an IP version 4 address, which you're all familiar with. There's 4As, which is the type for an IP version 6 address. There's a CNAME type, which is an alias. So you can have a machine having two names, and CNAME, which stands for canonical name, allows you to have an alias specified in the DNS. A really important one is this MX type. This contains the IP address of a server to use for email. So your machine, when it wants to send email to a particular host, it looks up the host in the DNS and looks for its MX record, and that tells you which mail server to send your mail to when it's going to this to the destination host. There are quite a few others. You can put actually any text information you like in the DNS. There is a catch-all one, which is just TXT. There are various others. There's a catch-all one for different sorts of services, and so on. There's a lot of information that can be stored in this distributed database. The advantage of having this database distributed is that because each node is responsible for the names in the node, in the zone, it means that the management is also distributed. So for example, where I am at the University of Sydney, it manages the sydney.edu.au zone and updates the DNS when new machines are added or removed within that organisation. And if anyone wants to find out the address of a node within the University of Sydney, the query will eventually percolate down to the name server for that domain. This makes it very, very efficient. So that's an introduction to the domain name service. And in the video I talked about the general idea of namespaces and specifically internet namespaces. But I've also described domain names, the domain name hierarchy, the DNS itself, this distributed name server or distributed database, which has name to address mappings, and the database records that it contains. This series will continue with videos on other core network protocols, but also application protocols, microservices, and computer network security. So for more simple applications of aspects of computer systems, please subscribe to the channel.